Swayam Prabha. Digital India. Educated India.
This maritime engineering, as you see, is a very special program which has got multidisciplinary input from mechanical, civil, structural, aerospace, naval architecture, chemical engineering, electrical, electronics, applied mechanics. It's a multidisciplinary program. You will find this program is completely different, dedicated to industrial training and thorough capacity building on the new trade of maritime sector. It's a grooming economy which will give you a lot of job opportunities and research frontiers as far as India is growing. And the Blue Corridor effect, which is planned by Government of India, is one of the important mission which requires maritime engineering growth to happen in the country. So this program caters to expected that capacity building in this program.
Friends, this is part of a material science engineering laboratory which becomes one of the teaching aid for the maritime engineering program. So when you talk about materials innovation in maritime industry, though concrete and steel have been conventional candidates of choice for engineers, for example, we have titanium vessels, high-speed craft boats made of fiberglass. These are all advanced materials which actually do not come across conventional standard design code of practices. We conduct box furnace test, tube furnace test, vacuum arc melting, induction melting, vacuum induction melting, vacuum sealing unit, which are all present in this laboratory is a small segment of material science laboratory. Friends, a typical furnace where the operating temperature for testing specimen can go as high as 12 degrees Celsius. Generally at room temperatures and ambient condition, the mechanical properties will not alter much. As you see in the course lectures, you will notice that strength of the material get degraded when the temperature rises beyond 600. Therefore, when you talk about fire resistant design, you must also choose an alloying element such a manner that the strength doesn't degrade beyond 600 degrees Celsius at all. Welcome to the ambience of IIT Gandhinagar lecture theatre. This is one of the interesting classrooms where the maritime engineering classes will be conducted. We have got state-of-the-art projection facility and good audio-visual recording systems. Once the lecture is over, you see the system here. We can generate the PDF files of the lecture directly and you can email the PDF files directly to your email IDs. So it's a state-of-the-art facility we have in IIT Gandhinagar where the lectures are lifetime recorded and shared with the students immediately. This is the IIT Gandhinagar library. This has got all collections of books which are referred as the standard textbooks and references for the course and the program. It also has lot of online editions of design code of practices and reference materials and e-collections of various video lectures of international courses and programs related to maritime engineering. We will be taking you around to the advanced material manufacturing units. So you will have state-of-the-art facilities available at IIT Gandhinagar. So welcome to the program to join MTech and PhD at IIT Gandhinagar Maritime Engineering. So please try to enjoy and take the advantage of this to the maximum. Welcome to the program and welcome to IIT Gandhinagar.
Hello everyone, welcome to lecture 33 of the course Marine Renewable Energy Systems, Analysis, Design and Development. I am Dr. Basangoda I. Patil, Assistant Professor, Department of Civil Engineering, PDU, Gandhinagar, Gujarat. In this lecture, we will discuss about TSUSUCA dolphin and its hydrodynamic performance and energy harvesting characteristics. It's a novel bio-inspired floating offshore platform developed as a multi-utility system. TSUSUCA stands for Tsunami Protection, Solar Power Utilization and other coastal application. The concept combines several functions within a single offshore structure. Under normal sea states, the device operates as a wave energy converter by utilizing the heave and pitch motions of the dolphin shaped body. The wave induced motion is transferred to a power takeoff mechanism for electricity generation. In addition to wave energy harvesting, the platform can also support solar panels for hybrid renewable energy generation. Another unique feature is the ability to function as a tsunami protector barrier when multiple units are deployed along the coastline. The bio-inspired dolphin geometry also offers this offshore tsunami protection feature, and then it can also act as a recreation and tourism center and provide training for seasickness. The figure on the right side shows various parts of the SUSUCA dolphin, including floating body, floats, hinged tail connection, power takeoff system, and supporting base structure. The concept is protected through an Indian patent application and represents an effort toward developing multi-functional offshore renewable energy infrastructure. Before studying the hydrodynamic performance, let us briefly understand the geometry and working principle of the SUSUCA dolphin. The device consists of a dolphin-shaped body connected through a hinged arrangement to a fixed supporting deck. The overall body length is approximately 32 meter with a width of 6 meter with draft of about 1.75 meter. The center of the gravity of the floating body is carefully positioned to achieve stable hydrodynamic behavior and efficient motion response under wave excitations. The structure is installed in deep water conditions, and the hinged connection shows the floating body to undergo primarily heave and pitch motions when waves interact with the device. As waves propagate through the structure, the floating body oscillates vertically and rotationally. These motions are transferred to the power takeoff system located near the tail section, where mechanical energy is converted into useful electrical energy. These figures on the right side shows numerical model from ANSYS Aqua. When the body is freely floating, it will float like this, and when high amplitude wave hits the nose of the dolphin, it more or less lifts vertically like this, deploys vertically like that to act as a coastal protection device. The preliminary dimensions and configurations were selected based on the earlier design recommendations and subsequently refined through the numerical investigations. The slide presents the simplified equation of motion used to understand the dynamic behavior of SUSUCA dolphin. The device is idealized as a hinged floating body, where the dominant response occurs mainly through heave and pitch related motion. For the simplified single degree of freedom representation, the free undamped vibration equation is written in terms of angular displacement theta. Here, this is the equation of motion for a idealized single degree of freedom of SUSUCA, where Ig is the mass moment of inertia of the SUSUCA body, and m is the mass of the SUSUCA, L is the distance of the CG of SUSUCA from the hinged point, and K represents the stiffness, and theta represents angular displacement in degrees. This equation helps us to understand the natural dynamic characteristics of the system. On the right side, the time domain heave motion equation is shown. The acceleration response of the body depends on the balance between wave excitation force, radiation force, and buoyancy force. In simple terms, the wave excitation force drives the motion while radiation and buoyancy force resist or restore the motion. Therefore, this formulation provides the basic theoretical background for studying the heave response, pitch response and energy harvesting motion of TSUSUCA dolphin. After completing the numerical investigations, a scaled physical model of the TSUSUCA dolphin was developed for experimental testing in a wave basin. The model was fabricated to a scale ratio of 1:15 based on the Froude similarity principles. Froude scaling is commonly used in offshore and marine hydrodynamic studies because it preserves the relationship between inertial and gravitational forces. As shown on the left, all major geometrical dimensions of the prototype were reduced according to the scaled factor. All these dimensions shown in this figure are scaled according to the considered scale factor 1:15. The full scale of the body length of 32 meter was represented by an approximately 2 meter long model while maintaining the essential hydrodynamic characteristics of the original design. Particularly, attention was given to preserving the center of gravity, buoyancy distribution and overall stability characteristics, so that the scaled model would realistically reproduce the motion of the prototype. The figure on the right side shows the fabricated TSUSUCA dolphin model together with the experimental support arrangement, where two dolphins in tandem are connected to the fixed base with the hinged connection here, and the power takeoff mechanism, linear power takeoff systems were connected to tail of the dolphins and mounted on the deck. This physical model enabled the measurement of motion responses, power takeoff behavior and energy conversion performance under controlled regular and irregular wave conditions. The combination of numerical simulations and physical experiments provides a more comprehensive understanding of the device performance. In this slide, we study the numerical study and its details, such as hydrodynamic details of the TSUSUCA dolphin. The table on this left side summarizes the key hydrodynamic properties used in the model. The device was analyzed in a water depth of 150 meter and total mass of approximately 102,490 kg, and the center of gravity was located at a distance x. In x, it is 10.423 meter, while the draft of the structure was 1.75 meter. The model also incorporates the mass moment of inertias about principal axis, which are important for accurately predicting floating body motions. Additional parameters such as body area, water plane area and volume of the water displaced were calculated and provided as inputs for the hydrodynamic simulations. On the right side, the response amplitude operators or RAOs for heave and pitch are presented. An RAO describes how strongly a floating structure responds to incoming waves at different frequencies. The heave RAO shows two dominant response peaks indicating resonance regions where vertical motion becomes significant. Similarly, the pitch RAO exhibits pronounced peaks near the natural frequencies of the structure, suggesting enhanced rotational response under those wave conditions. Between these peaks, the response reduces considerably, indicating frequencies where the structure is less sensitive to wave excitation. These RAO characteristics are extremely important because they help identify the operating wave frequency range where maximum energy extraction can be achieved and where structural loads may become critical. The hydrodynamic analysis therefore provides the foundation for evaluating motion behavior, power takeoff performances, and overall wave energy conversion efficiency. And in this slide, we see the free decay responses in heave and in pitch, computed numerically using ANSYS-EQUA and calculated natural frequency. Heave natural frequency is 0.554 radian per second, and in pitch it is 0.793 radian per second, and damping ratio in heave it is 4.04% and pitch it is 2.03%. This slide we study the behavior of SUSUCA dolphin under irregular wave conditions, which more closely represents real ocean environments. As indicated on the left, wave frequencies between approximately 0.4 to 0.81 radian per second for irregular waves and 0.6 to 0.7 radian per second for regular waves are considered for the study. The plots on the left on this side shows the time history of the heave displacement for about 5-meter wave and 11-meter wave. These are irregular waves for a simulation duration of about 1000 seconds. For the 5-meter wave condition, the structure exhibits moderately oscillatory motion with varying amplitudes, reflecting the random nature of the incoming wave spectrum. And as the wave height increases to 11 meters, significantly larger heave exertions are observed, indicating greater energy transfer from the waves to the floating body. And these 5-meter and 11-meter wave heights are considered to study the coastal protection ability of the SUSUCA dolphin, whether it will be able to deploy vertically or no. To understand this motion characteristics, more or less nearly tsunami wave heights are considered just to see its deployment when the high amplitude wave hits them. Then the figure on the right side again presents the corresponding power spectral density plots. These two are power spectral density plots for 5-meter wave and 11-meter wave. The orange dashed line here represents dominant wave frequency, approximately 0.554 radian per second, while the black dashed line indicates the peak response frequency around 0.628 radian per second. It can be observed that peak structural response occurs close to the dominant wave excitation frequency, demonstrating effective interaction between the incoming waves and the device. The PST peaks become more pronounced under the 11-meter wave condition, confirming that larger waves induce stronger dynamic responses and greater energy absorption potential. The table here summarizes angular displacement response under different irregular wave heights. The maximum angular displacement increases progressively from approximately 42 degrees for a 5-meter wave to about 74 degrees for an 11-meter wave. This trend indicates that SUSUCA dolphin remains highly responsive across range of sea states, which is advantageous for wave energy harvesting, although larger motions must also be considered in structural and survivability assessments. Overall, these results demonstrate the capability of the device to effectively respond to realistic irregular wave environments while maintaining significant motion amplitudes required for energy extraction. On this side, I present one of the important response analysis carried out for SUSUCA dolphin, namely the quadrilogarithmic plot of the heave response of SUSUCA dolphin under irregular waves of height 11 meters and wave period of 10 seconds. This analysis was developed to understand the combined influence of displacement, velocity and acceleration on the dynamic behavior of the platform. The horizontal axis represents the frequency ratio beta, which is the ratio of wave frequency to the natural frequency of SUSUCA. The vertical axis represents the pseudo velocity, while the two inclined axes corresponding to the pseudo acceleration and displacement. Through the relationship shown on the right side, all three response quantities can be visualized simultaneously on a single spectrum. The orange curve represents the input spectrum here. This is the input spectrum, whereas this curve here represents the response spectrum of the SUSUCA. An important observation is that the response spectrum is significantly higher than the incoming waves. This indicates that the geometry and the motion characteristics of SUSUCA amplify the heave motion, which is desirable for wave energy extraction. Another important point is the location of the peak response. The input spectrum peaks at a frequency ratio of approximately 0.097, whereas the heave response spectrum reaches the maximum near 0.975, which is very close to unity. This suggests that the structure is operating close to its most effective dynamic response region, thereby maximizing energy capture from incident waves. For example, at point S shown on the spectrum, the pseudo displacement is about 3.3 and pseudo velocity is about 7.73 and pseudo acceleration is about 1.6. These values provide a qualitative understanding of how displacement, velocity and acceleration contribute to the overall response at that frequency ratio. Overall, this logarithmic representation helps us identify whether the response is governed by mass or stiffness or damping effects and provides valuable guidance for future optimization of the SUSUCA dolphin design for enhanced wave energy harvesting performance. After completing the numerical investigation, the next important step was to experimentally evaluate the performance of SUSUCA dolphin in a controlled wave basin environment. These photographs here present the scaled SUSUCA dolphin model tested at the wave basin facility at IIT Madras. The objective of these experiments was to understand the actual hydrodynamic behavior of the system and to verify the desired heave and pitch motions could be achieved under realistic wave conditions. The experimental program included both regular and irregular waves. For regular waves ranging from 5 to 20 centimeter height and 1.5 to 2.5 seconds time period were considered. when scaled to prototype dimensions, in actual they represent 0.7.5 meter to 3 meter in natural sea. Using Froude similarity, these corresponds to approximately the stated wave heights here, 0.75 meter to 3 meter in natural sea. Similar ranges were adopted for irregular wave investigation with a wave heading angle of 0 degrees. Before conducting the wave tests, free decay experiments were performed. In these tests, the model was displaced and released, allowing it to oscillate freely. From the measured response, the natural frequencies in the heave and pitch modes were determined as 6.742 radian per second and 5.348 radian per second respectively. These values are important because they help identify the dynamic characteristics of the platform and guide the selection of suitable operating wave condition. The images show the instrumentation and the power takeoff arrangement attached to the model during testing. So, here the two dolphins were tested in tandem. So, and the 4 linear power takeoff systems were connected, 2 for each dolphin, and the nose of the dolphins were rested on the floats, and complete power takeoff mechanism systems are mounted on the base, fixed base, and 2 dolphins were connected to the base, fixed base using hinged connection, and the data acquisition system is mounted here, which is collecting the responses using MRU, which is mounted on the top of the dolphin, and under the action of waves, the oscillation of 2 dolphins in tandem is shown here. Vertical motion of the body generated relative movement in the PTO system, enabling energy extraction while simultaneously providing valuable information on the motion response of the platform. These experiments played a crucial role in demonstrating that the bio-inspired TSUSUCA dolphin is capable of achieving significant heave and pitch oscillations under wave loading, thereby validating the fundamental concept of wave energy harvesting and providing confidence in the numerical predictions discussed earlier. And this video shows the motion of 2 dolphins in tandem when tested in the wave basin. Under the action of particular wave height and particular wave, the 2 dolphins are moving like this, which giving the relative motion in the PTO attached to them. This is the video captured during the experimental test at IIT Madras wave basin. And the top view of the test setup looks like this. The wave basin was of size 30 meter by 30 meter, and from the wave maker or wave paddle, the dolphins were mounted at a distance 12 meter to avoid the reflection losses. Also, they were almost mounted in between the square wave basin to avoid the reflection losses due to reflected waves. And here is the absorber, and data acquisition system DAQ is mounted on this truss bridge, and wave probes are placed here. One wave probe is here and another wave probe is here to measure the incident wave elevation, and the side view of the dolphin is like this, where when the wave approaches and hits the nose of the dolphins will have heave motion initially, then this heave will move the tail linearly to and fro like this, and this will will be captured by linear motion electrical generator LMEG, and overall depth of the wave basin was around 3 meter. And the power generation is by linear motion electricity generation, and it has these parts which were discussed in the previous lectures also. So, the main part was the moving rod, which is a steel rod with high power N52 neodymium magnets, and then there is a cylinder which is having a copper wire windings inside which the steel rod, magnetic steel rod will move to and fro, and because of this electromotive electromotive force is generated, and the electricity is measured or voltage is measured by the multimeter connected to the copper wires endings, and then these were the LMEGs which were connected to the two dolphins in tandem. Two LMEGs for each dolphin. So, total 4 LMEGs were involved in harvesting power. And this is the overall working of the SUSUCA dolphins in the wave basin stage by stage. The first one, SUSUCA dolphin moves up and down under the wave action. This is the up and down motion, and then to and fro movement in LMEG due to hinged connection between SUSUCA dolphin and the base truss. That is, on the base truss LMEG is mounted and there is a to and fro motion here. Then steel rod moving, steel rod having magnet moves to and fro in the cylinder. Then an electromotive force is generated due to movement of the steel rod and inside the hollow cylinder wounded with copper wire, producing the electricity. And the regular wave incident power is calculated by using the standard expression P incident equal to 1 over 8 rho g h square into half C into 1 plus g, where P incident is the wave power flux watt per meter and h is the wave height in meter, and this term half C into 1 plus g is the group velocity, and WC is the capture width which will be used in the further calculation. And irregular wave incident power is as per the ITTC guidelines, which is P incident is equal to 1 over 64 pi rho g square hs square and TE, where incident wave power is captured by P incident into the capture width WC. Then the kinetic energy is calculated by using half m Vt square, where m is the mass of the LMEG plus dolphin, which was around 48 kg for each experimental model, and Vt is the velocity at any time in meter per second. Then power absorbed by the SUSUCA in watts is calculated like this: P SUSUCA equal to rate of change of kinetic energy. Then electrical power output is calculated by ratio of V square upon R, where P electrical is the electrical power in watt and voltage measured in volts, and R is the resistance of copper wire. This R is calculated using this expression rho C into L by A, where rho C is the resistivity of the copper, which is 1.68 into 10 raised to minus 8 ohm meter, and L is the wire length meter and A is the cross sectional area of the wire. And hydropower efficiency of the SUSUCA is calculated like this: eta H equal to power absorbed by the SUSUCA over power captured into 100. Then electrical power efficiency eta E is calculated by the average electrical power produced by LMEG or power captured into 100. Let us now understand some representative experimental results obtained under irregular wave condition, where the incident waves were generated using the widely adopted Jones-Webb spectrum. The top row corresponds to set 1, which is 5 centimeter and 1.5 second waves. The bottom row corresponds to set 6, corresponds to 15 centimeter and 2-second waves. For each test case, 3 important outputs are presented. The first plot here shows the time acceleration time history of the SUSUCA dolphin. We can observe that the response amplitude increases significantly when the wave height increases from 5 centimeter to 15 centimeter. This indicates that the floating body is effectively responding to the incoming wave energy. The second plot here in both the cases indicates the power spectral density or PST of the Hue motion. The red color line, dashed line, indicates experimentally determined natural frequency in both the cases of the system, approximately 6.747 radian per second. In set 1, the dominant energy peak are located close to this natural frequency region, demonstrating efficient dynamic excitation. In set 6, a strong spectral peak is observed, indicating a higher concentration of wave energy being transferred into the motion of this device. The third plot shows the instantaneous power absorbed by the linear motion electricity generator, that is LMEG, under the smaller wave condition. The absorbed wave power remains relatively low, typically below about 1.5 watts. However, when the wave height increases to 15 centimeter, the absorbed power rises subsequently, reaching the value of several times of watts, with occasional peaks approaching 80 to 90 watts. The key observation from this slide is that higher wave heights produce stronger Hue responses and significantly greater power absorption. The PST analysis also confirms that the selected geometry and dynamic characteristics of SUSUCA dolphin allows the device to effectively interact with the dominant wave frequencies present in the sea state. These results provide experimental evidence that the proposed bio-inspired platform can successfully convert wave-induced motion into useful electrical power while maintaining stable hydrodynamic behavior under irregular ocean waves. Lastly, overall energy conversion performance of the linear motion electricity generator, that is LMEG, under all 8 irregular wave condition generated using Johnson spectrum is shown here in this table. This table summarizes the 5 important parameters: the incident wave power in watts, and the average hydropower absorbed by the LMEG, and the average electrical power produced, and the hydropower efficiency and the electrical power efficiency. A clear trend can be observed as we move from set 1 to set 6. As the wave height and available wave energy increase, both the absorbed hydropower and generated electrical power increase substantially. For example, in set 1, the incident wave power is approximately 1.94 watts and the electrical power produced is only 0.45 watt, corresponding to an electrical efficiency of about 23.56%. As the wave condition becomes more energetic, the device captures more energy, more wave energy. The best performance is obtained in set 6, highlighted in green color. Under this condition, the incident wave power reaches to 23.26 watt, while the LMEG absorbs 7.85 watts of hydropower and produces 7.45 of electrical power. This corresponds to a hydropower efficiency of about 33.73% and an electrical efficiency of 32.04%, which is the highest value recorded during the experimental campaign. Interestingly, an interesting observation is that efficiency does not continuously increase with wave power, although set 7 and set 8 are have higher incident wave power. Their efficiencies reduce to about 26 and 17% respectively. This indicates that beyond an optimum operating condition, the motion of the system becomes less favorable for efficient energy extraction. Therefore, the experimental results suggest that SUSUCA dolphin possesses an optimum operating range where the interaction between the wave excitation, floating body motion and generator characteristics is most effective. Overall, these results are significant because they demonstrate that the bio-inspired SUSUCA dolphin can achieve electrical conversion efficiencies exceeding about 30% under irregular wave conditions, validating the feasibility of the proposed wave energy harvesting concept and providing confidence for future prototype scale deployment. And overall, the summary of this lecture, in this lecture we have introduced bio-inspired SUSUCA dolphin concept and discussed its multifunctional applications in wave energy harvesting, tsunami protection and offshore sustainability. And then we studied the hydrodynamic behavior of the system through numerical studies including free decay analysis, RAOs, PSTs, angular displacements and quadrilogarithm response spectra. We then reviewed the experimental investigations carried out in a wave basin, including the LMEG based power takeoff system, regular and irregular wave testing and the resulting power generation characteristics. And the results demonstrated that SUSUCA dolphin can achieve electrical conversion efficiencies exceeding 30% under optimum irregular wave conditions, validating its potential as a next generation multi-utility offshore platform. Thank you for your interest. Thank you.